All right, everyone. This is gonna be my third time recording this because I realized my first two times were a little too long, and we don't have that much time in class, so kind of have to redo it. Um, so basically, today we're gonna be talking about graphs. Very exciting, right? So what a graph basically is kind of a set of nodes and vertices. We can call like this a node. So node would be like one of these circles, and then a vertice would be, you kind of learn from your math class, right? Vertice would kind of be one of these edges right here. So the graph is a set of these nodes and vertices. So our nodes would be A, B, and C, and D, and our vertices would be these little lines right here. And what a graph basically allows us to do is connect like these nodes in unique ways. So like we can have some graph that looks like this, some graph that looks like that. They're all different and they kind of represent different things in life, like airplane routes, stuff like that. And say that's like Moscow, that's like Atlanta, etc. You can see these like routes and what they connect to and if they don't connect at all. So what we're going to be doing today is called a breadth first search algorithm. Um, the kind of end goal of it is to return like a list, just some list like that in some specific order that you're gonna see the what like what the order is when we actually do the algorithm. So our kind of goal is to like let's say we're gonna start from A, right? This first one right here, because A is the first letter of the alphabet. It's top of the graph right here. So our kind of goal is to like spread from A to these other nodes and kind of just like return it as a list, um, just to show like what all the nodes in the graph are in a specific order. So yeah, we're just gonna go ahead and start. These two don't really apply to our graph right here because we clearly have a start and we clearly have a graph right here. So we're just kind of ignore those. If we didn't have a start or if we didn't have a graph, then we're gonna throw an exception, but it doesn't really matter here. So what we're gonna do is these right here. We're gonna create two different data structures. One is gonna be called visited, and one's gonna be called a queue. Visited is gonna be called, or it's just gonna be a set, and the queue is gonna be a queue. So what that means is a set is basically a list. So this would be a set right here. But the unique thing about it is there's no duplicates in it. So like if we had two C's in this, that wouldn't be a set, right? And what a queue basically is you can think of a Chick-fil-A line, right? Um, so we have like four people here. Um, this guy would be the first one to order. He kind of entered the line first. This guy just entered the line, right? So if we want to kind of remove someone to make them go order at the you know the kiosk or whatever, we're gonna remove them from the queue. He no longer is in our queue. He's going to order. And if someone new comes into the line, we're kind of adding them to back. We don't want to add them to the middle or the front because that's just kind of rude. We keep the the line structure right, and you don't want to cut the line right. That's not a good look. So yeah, that's what a queue is basically is, and we're just gonna call one of them visited and one of them just queue, just for simplicity terms. Um, so once we do that, we're gonna execute this line right here, which says we add the start node, which we're just gonna call the start A. We're gonna add the start node to visited and queue, so we're just gonna do that here, plain and simple. Um, So what's going on over here is we kind of have two different loops. One's the while loop and one's a for loop. So what a while loop is it kind of runs until a certain condition is met. So that condition here is while the queue is not empty, this loop's basically going to keep running. And then this for loop right here is it's kind of to once we get to like let's say we start at A, right? Um, what this basically says is for all like the adjacent vertices to current, which is going to be A once we run the code. Um, we're gonna let's see for all the adjacent vertices, we're gonna do a specific thing. So it's gonna run through all the adjacent vertices. So you can see B is the only adjacent vertex to A because it's the only connection we have here. It's the only line that we have here. If this line was drawn right here, A would also have a connection to C, so that would be another adjacent vertex. But we don't have that. So yeah, we're gonna kind of start this loop right here. Um, while the queue is not empty, so we can clearly see the queue is not empty here. So we're gonna kind of run this loop, this while loop. We're gonna remove the last element from the queue and call it current. So we're just gonna kind of move this guy down here. Um, And then for all the adjacent vertices to current, we kind of explained that B right here is the only adjacent vertex. We're gonna define B as neighbor, just to and if the neighbor is not in our visited set, this line right here, we're gonna add neighbor to Q and visited. So we're just gonna add B right here because it's not in this set already. It's not in this set here like before we added it. So yeah, so we're gonna run through this for loop again, but we see that there's no other adjacent vertices, right? B is only adjacent one, so we're gonna kind of stop this loop and then go back to this top loop right here. While the queue is not empty, so we can see the queue is not empty, so we're gonna run the while loop. We're gonna remove the last element, B. Yeah, we're gonna remove the last element B and call that current. Yeah, and then for all the adjacent vertices to B, you can see that the adjacent vertices would be C and D because there are two connections right here. So for all of these vertices, so we're just going to iterate through C and D. We're going to define, so let's say we start with C, right? Because it's lexicographically before D. So we're going to define C as our neighbor. Yeah. We're gonna find C as a neighbor, and if neighbor is not in the visited set, which is clearly not in there, C is not in the visited set. We're gonna add neighbor to the queue and the visited set. So we're just gonna add C over there and there, and then we're gonna go back over here, and we have another adjacent vertice, which is gonna be D over here, right? Because D is also directly connected to B. So for that vertice, we're going to define it as neighbor. And if neighbor is not in our set, wait, sorry, I meant to write D. If neighbor is not in our set, we're going to add neighbor to the queue and visited. So we're just going to do the same thing. We're just going to add this to here and here. All right, so there's no more adjacent vertices to B, so we're going to kind of stop this loop and go back to the while loop here up top. You can see our queue is not empty. We have C and D in it, so this loop's going to run. We're going to remove the last element from it. So we added C first, so we're just going to kind of remove that here. And we're going to call that neighbor. So let's say C right here. If neighbor's not a visited set, which it kind of is right here, so we're not going to execute this because it's not in our, or it is in our visited set. So this condition is not true. So we don't run the if statement. So we kind of just go back to the top right here. Basically, what we're going to do is just remove D from the queue. Same thing happens to D as did to C. So we're just going to remove that, call D the neighbor. D is clearly in our set right here, so we're just going to stop the loop. And so now these two loops are kind of terminated because there's nothing in the queue and there's no adjacent vertices to nothing. So it kind of just doesn't really exist. So you can see our last line here is to return visited. So yeah, we're just going to return this right here. This kind of, it's a basic traversal of our graph just to give, some sort of direction that we start from the top right here and we kind of expand outwards one by one at a time. So you can see like A is the top right here, and then we kind of add B right here, and then we kind of explore from B to C and D. So C and D are here. And honestly, we can switch C and like D and C right here. It doesn't really matter about these orders because they're kind of like in the same distance from A. So like this has a distance of 2 because there's 2 edges from A to C, and this also has a distance of 2 because there's 2 edges from A to D. So yeah, that's the algorithm. Hope you all have a great day.